Hello everyone, today I'm going to deliver another lecture on deflection calculation by virtual work method or unit load method for beam. This is for beam. So first of all, the course content in I will try to cover first of all the theory of virtual work method on or unit load method for beam, and second one in example of virtual work method or unit load method for beam. Okay, so let's see the theory of virtual arc method or unit load method for beam. So it could be a flexural method also. Okay, so here the deflection due to flexural deformation. The flexural deformation is main source of deflection in many civil engineering structure like beam, slab, frame. So those design is primarily against bending moment. So it is often such significant than other causes like axial shear, torsional deformation. So equation is given here. Deflection is summation of U into dl. U means load and del into dl into is given. So previously section we have been seen principal virtual work delta equal to summation of U into dl. So where the delta is above indicate the deflection or rotation in body, is the virtual internal force in the element of the body, which is deformed by the amount of dl in the direction of u. So deflection of beam or frame due to flexural load. So we know the flexural deformation use the virtual internal moment m1. So it's given in the element where dl is the rotational delta dl caused by the external force, which is del L equal to rotational, which is curvature into dx. We can say m not divided by el into ds. So in this case delta equal to summation of m1 m2 into divided by ei ds is comes, where m1 is a moment bending causes external force. EI is called the flexural rigidity of the member. Here the integration of sign is used the summation of, because the bending moment of vary where the length causes by unlike truss where the axial force do not vary within the member. Okay, so we can solve this problem using this formula, or we can use the integral table. So this is the integral table. So integration production of function of summation of f1 f2 ds. So in this lecture I will just covering using this formula to solve this question. Okay, so let's see here. Determine the displacement at point B. This is the 10 feet cantilever beam. So B is the midpoint of the beam shown in given. EI is given 200 gigapascal. I is given 500 in 10 to the power 6 millimeter to the power 4. Use the virtual work method or unit load method. So as we know, the these are we have to divide this diagram. One is real one is real force, in another one is the virtual load. So we can see here the real force here, and the virtual load is one is applied, is where is some where is asked as the point B is asked, the virtual load is applied at the point B. Okay, so in this case as we know, we are using this formula summation of m1 small m into block m divided by L. Small m, what is the small m? Small m is a virtual force, and what is the bigger m? The block m is the real force, as we have been seen here. Here, but it is donated m1 in m0, but I am donated small n and block m. So so block letter m, as we have been seen here, the real force, the all forces are given. So at first I am dividing this portion BC. So BC I am taking the moment of this point, as we have been seeing here. So if the taking the moment is here, so as we know, the this is the 12 kilonewton per meter. So the load is 20 kilonewton per meter into distance is given x1, and as this is the UDL, so it will be x divided by 2, x divided by 2. So this is the force UDL. So as you all know, this is the force 12 into x. This is the force as the UDL is converted to the force, and it will be act on the UDL divided by 2 as the middle portion, which is x divided by 2, and we have been found 6 into x square. So for virtual forces, so as we applied at B point as asking displacement point B. So if we calculate here, the moment is cutting here, that there is no load, that's why small m1 equal to 0. Okay, so let's see again for real truss for m2 how we'll calculate m2. M2 will be this portion, which is AB, from the left to right. So we are taking the from the left to right. This is the portion, so we can see that this is the portion, this here. So here, so if we calculate here m2, we are taking the moment is here. At first I am taking the m into 5 as the given is 5. So this portion is 5, this portion is 5 into x2. X2 mean this portion as is shown in I am showing in figure. So these are the load, and it will be acting on the perpendicular distance. What will be distance? Distance will be this distance divided by 2. So what will be this distance? This distance is 5 into x2. So this is the 5 into x2. As we've been seeing, this is the 5, and it will be gone here. So 5 into x2, it will be divided by 2. Okay, so in this case we have been founding this equation. For the virtual forces, we have been seen here, one load is applied on point B as is here. So for m2 we have been calculating from this point to this point as we have been seen as per our requirement. So I am taking a moment from here as is here. So there is no load, only one kip load is applied. So one kip load, but distance is x2. So there the least distance x2. This is the small m2. Okay, so we have been getting four value, which is bigger m1 for real truss, and virtual one which is the small m1, and another we have been found m2, bigger m2 or block letter m2, and found the small letter m2. Now we are putting this all this value is this equation, as we know the displacement point at B. This is the point B as asking for the question. This is the point B as the middle of the cantilever. So as we have been integrating 0 to L. 0 to L means this total length as we have been shown in figure 5 into 5 into 12, and summation m into m, as I am already said. Small m is taking from the virtual force, and the bigger block letter m is taking from the real forces. So two forces, one is a virtual force, another diagram is the real force diagram. Okay, so let's see here. At first I'm taking bigger m. EI is common, as we have been on the wall. EI is same as it is as first 6 x square. So this is the bigger m. So bigger m or block letter m into small letter m. Small letter m is 0. This is the 0. So it will be writing in here bigger m into smaller m, but I am just writing the small m first and then bigger m later. So there is no issues at all, I think. So bigger m we have been found here, m1 6 into x square here, and smaller m we have been found 0, so it will be multiplied with 0. So all this portion, if we multiply to 0, that will be 0. So another portion we have been founding here. here m2 we have been seen 6 into 5 into x2, 6 into 5 into x2 into x, and it will be multiplied into smaller m. This is the smaller m. So this portion is smaller m, or we can see the virtual forces, and another we have been seen here the bigger m or block letter m. It is come also from real forces. So if we multiply with then what will be happen? So it will be 5 into 5, it will be 25, and 5 into x into 5x, another one to 5 into x into 5x, and x into x square, and it will be also remain x. After calculating here, we can see 25 is remain here, and 6 is taken here. We can see 6 is taken in the common, that's why we are not multiplying. And 5 into 5 is 10, this is the 10, and x square is remain same. Now we can as usually we can multiply to this x and finding this value. After finding this value, we just putting the integration 0 to 5. Why? Because another 0 and 5, this is the first portion. If I am changing color, it's the multiply of here 0 to 5. That means this portion b to c, these are the 0 to 5, and another portion is a to b, this is the 5. So 5 into 5 equal to 10. That's why so you cannot mix up that the integration 0 to 10, because the length is we are divided 0 to 5. Okay, so in this case we are just integrating theirs, as we know 150 into x, which is n into n to the power n into n plus 1. So n plus 1 into 2 divided by n plus 1, which is 2. N into n plus 1, n into n, which is 2 plus 1 into 3, and divided by 3. And in the same as n into n plus 1, which is n is given is 3, n plus 1 is 4 divided by 4. So putting the limitation, which is 5, and here, and then finding this value. Now we will calculate the putting the EI, which is flexural rigidity. So don't mix up the unit. So unit is given is gigapascal and millimeter to the power 4. So so gigapascal means kilonewton per meter square, and we are just converting all things in m to the power 4, and found 2.09 inches square. Okay, so we can see the this beam will be divided. Sorry, I'm just, if I change the color here, then it will be acting like this, and this portion will be 2 inches square. So we've been seeing here 2.09 inches square will be deflected at point B, not the free end. So if we see that the same math is what will be deflection at point D, at free end, which is called C, the free end. So it will be must be greater than 2 inches. So let's see here the same math is given here. So we've been seeing this is the real frame, and this is the virtual frame. So real frame, we are taking the moment is here, so x1. So if we calculate here, I'm sorry. Okay, sorry. So it's okay. So if we taking the moment is here, so there is no portion A and B. In the previously we've been seeing there is a two portion A and B, as we've been calculating A and B. But in this case there is a one portion, but length is the same. It is 10 feet. Sorry for that. Okay, now we are seeing here, we are taking the moment x1. This is the x1. So if we are calculating x1, so moment 10, 12 into x, this is the force, and it will be acting on force divided by 2. This is the force divided by 2, and minus 6s square. In the same as we have been taking the displacement at point B, so we are just cutting is here, and after cutting we are applying the unit load is 1, so it will be x1. So m into 1 plus x and minus, it will be x1. Okay, so we are signing giving sign here. So all the sign minus 6 and minus 6, it will be minus into minus will be plus. We'll see how will occur. So as we know, delta b, which is deflection at b and 0 to L, it is the limiting value. 0 to L, the length, the distance, and m into m is the virtual diagram. This is the virtual diagram, and bigger m is the real diagram. Okay, so virtual diagram we've been finding -1. This is the -1. We're just putting this value minus small m, and the bigger m we have been seeing -6, and we have been seeing -61, and putting all this value here. So we have been found minus into plus 6x cubed. So 6 is taken in left side, so x cubed. As we know, I will calculate n into n plus 1. N is 4, so n is 3, so 3 plus 1 into 4 divided by 4. We're just putting this value, the 10, and or ei value, so you don't forget to complete the I value to the m to the power 4, and putting 1.5 or 150 millimeter or 6 inch square. So the same we can see here. This is the 6 inch square. In the previous math we have been found 2 inch square. This is the 2 inch square, but these 2 inch square are found at the middle point of B. But the free int we have been found 6 inch square. These are the same math. We have been found 6 inch square at the free int. So if we divide it here, so we can found this is the 6 inch square. But in the middle portion we have been found 2 inch square. Okay. So deflection completed. So we can see another example. Determine the slope, or you can say rotation, at the point of B. This is the point of B at the beginning shown. EI is given same as it is. We have been use the virtual work method. Okay. So we can see we are dividing this diagram into real force, which is bigger m, and the virtual force is the small m. Which bigger m is given is m, and the small is m. What? So as the slope is B point, so we are just applying 1 kilonewton per meter and extra moment. Okay, so we are just taking the moment x1. So m into force into x, as we it is given the line load, which is kilonewton per meter. So 12 into x, and it will be acting on x divided by 2, as we have to calculate as a point. We have to consider as a point load. And m2, we are calculating m2 for this portion m2. So what will be happen? M2 12 into x plus 2. So this is the 5, and this is the x2. So that's why this is the load, 12 into 5 into x2, and the distance will be 5 plus 2. So distance we know this is the 5, and x2 it will be acting on the middle portion. That's why it will be 5 plus 2 divided by 2. And in this case we are finding this equation. In the same way we can see the virtual forces, as we have been taking the x1 here. There is no load, that's why m1 equal to 0. For the m2 cases, as we've been seeing here, the m2 is 1, but there is no external forces, as 1 kilonewton per meter is acting, as the asking slope is point B. That's why it is the virtual force, but it is for slope. But in the previous math we have been seeing the displacement is asking. When the displacement asking, then we have been applied the load. When the slope is asking, then we are applying the moment. So if you must be keep in mind here. Okay, so after finding this, and we know m into m is a small which is the virtual force, and real force is m. So we are just taking is here, and limitation 0 to 5 for the first portion, the BC, and second portion limiting 0 to 5, as it is. As we know, the bigger portion, bigger m, which is given 6, this value. So I'm just scrolling here. We are getting this value and this value, and we have been finding this value. This here 6 into x square, and m1 into 0. So if we multiply with 0, then all will be 0. These are the 0. this is the 0. And second portion, here m2 we've been found 6, this portion, and m2 equal to this portion. Just we are just multiplying this portion. If we multiply it 5 into as it is, it will be multiplied same as it is. And after finding this value, we are just saying x into x plus 1. So there is no load, that's why it will be x, as per rules of integration. This will be integration, and x to the power what? X to the power will be n into n plus 1. N is given 1 plus 1 into 2, and x square, which is x n plus 1, which is 2, plus 1 is 3 divided by 3. And after calculating all this value and finding this value as it is, and putting all this value and finding 0.027 radian, but it is found at point D, at point B, so it will be rotating, acting like that. So we can see the slope here, the slope theta b, it will be from 0.0275. In the same math, if we do here no, this is not a same math. Another math is given here, so we don't need. So if you have any question, let me know. I just summarize that. The summarizing is that there is the displacement point B, then we will take the real trusses, which is block letter M, and the virtual work we just apply 1 unit load. If we asking the slope at point B, then we are just applying 1 Q per kilonewton per meter moment, and after integration m into n and divided by ei and finding this value and putting all this value, then we have been found this, and we will also found this radian also. So thank you everyone, thank you. If you have any question, then let me know.